Hello and welcome back to Linear Algebra, the video series where we talk a lot about eigenvectors and eigenvalues. And in today's part 55, we will explain the term algebraic multiplicity. In some sense, it will tell us how often an eigenvalue occurs for a given matrix. But before we start with the definition, first I want to thank all the nice people who support the channel steady, here on YouTube, on Patreon, or by other means. And as a supporter, you can use the link in the description to see the full series about linear algebra. Okay, then let's immediately start talking about eigenvalues again, and we usually denote them by a lowercase lambda. And please recall, the set of all eigenvalues for a given matrix A is denoted by the spectrum of A. And moreover, we also know that the eigenvalues are determined by the characteristic polynomial. More precisely, they are given by the zeros of this polynomial defined by the determinant. And in the last video, we have proven one important fact for the characteristic polynomial, namely, if A is an n times n matrix, then this is a polynomial of degree n. Therefore, we can just use general facts about polynomials of degree n and say something about the eigenvalues. And that's where the important and famous fundamental theorem of algebra comes in. And it tells us something about solutions of a polynomial equation where the degree of the polynomial is n. So we have an x to the power n plus an minus 1 times x to the power n minus 1 and so on. Hence in the end we have anx plus a0. And now as before we want an equation, so we set this as equal to 0. In other words, we search the zeros of this general polynomial of degree n. However, degree n means explicitly that this first coefficient is non-zero. Otherwise, obviously, the polynomial would have a lower degree. Now, in addition, we can also put the whole thing into a general context and say that the coefficients come from the complex numbers. Indeed, the full power of the fundamental theorem of calculus lies in the complex numbers. Now, if you don't know a lot about complex numbers, you can check my video series about start learning complex numbers. There you can learn all the basics, and then you see complex numbers are not really more difficult than real numbers. However, they have some nice advantages, and one big advantage is this fundamental theorem of algebra. And it tells us that a polynomial of degree n has exactly n zeros in the complex numbers. Hence, we can simply enumerate the solutions of this equation and call them x1, x2 and so on. Now, the last one is xn, and in general, they all lie in the complex numbers c. So here you see, this is a very powerful result because it tells us no matter which polynomial we choose, which has degree greater or equal than 1, we always find solutions. However, please be careful, even if all the coefficients are real numbers, the solutions still could lie outside of the real number line. And indeed, that's the reason we need the complex numbers here, because just with real numbers it would not be correct. Moreover, what the theorem does not tell us is that all the solutions here are distinct. So indeed, two or more solutions could just coincide. However, it's still very useful to speak of n solutions then, because we can rewrite the whole polynomial. So if we call the polynomial p of x, then we can factorize it. This means that we have the leading coefficient an and then just linear factors. And inside these linear factors, we find the solutions x1 to xn. In other words, the fundamental theorem of algebra tells us that we have exactly n linear factors here. And there you see, if one solution occurs more often, it would just represent more linear factors in this factorization. And there I can already tell you, at this point the term multiplicity comes in. However, before we go into the details there, let's first draw some important conclusions for the characteristic polynomial. There, please recall, for a square matrix A, we define PA as the characteristic polynomial. So more precisely, PA of lambda is defined as the determinant from before. Okay, and now we can simply apply the fundamental theorem of algebra for this polynomial. First thing we can say, PA of lambda is equal to 0 has at least one solution in C. So we can't say that we always find real solutions, but we can say that we always find complex solutions. So this means if we expand everything to the complex numbers, we can conclude that a matrix always has at least one eigenvalue. However, the thing is, even for a real valued matrix, this eigenvalue could be strictly complex. And that's the reason why it's very helpful to expand linear algebra to the complex realm. Because there, the whole eigenvalue theory gets simpler. Okay, so for this fact here, I can immediately give you an example. Let's choose the 2 times 2 matrix given by 0, minus 1, 1, 0. For this one, the characteristic polynomial is a quadratic function. Namely, it's lambda squared plus 1. And we immediately see it has no real 0. Indeed, the 2 solutions we find are plus and minus I. So we could say the 2 complex numbers minus I and I are the eigenvalues of this matrix. And in fact, in the future, we will always do that. We will always include the complex numbers as eigenvalues. However, this whole expansion pack for linear algebra we will discuss later. First, let's also factorize our characteristic polynomial as the general polynomial from before. This means first we have the leading coefficient, which is always minus 1 to the power n. And then we have the linear factors with all the solutions involved, and now we call them lambda 1, lambda 2, and so on. In particular, now we know that we could simplify the whole thing if we knew if some linear factors would coincide. And of course, we know this can definitely happen, so let's look at an example again. So maybe let's keep it simple and let's take a diagonal matrix with 1, 2, 1, 2 on the diagonal. Then the characteristic polynomial can be written as lambda minus 1 times lambda minus 2 times lambda minus 1 again times lambda minus 2 again. Therefore, we can simplify the thing with powers 2. And exactly this exponent now we call the algebraic multiplicity of the eigenvalue. So for example, the eigenvalue 1 has the algebraic multiplicity of 2. And indeed, here we have the same for the eigenvalue 2 as well. So you see, this concept is not so complicated, and I would say let's put that into a definition. So now we already know the algebraic multiplicity tells us how often the eigenvalue occurs in the characteristic polynomial. So let's say we have an eigenvalue, a 0 of the characteristic polynomial called lambda I. So let's say we have an eigenvalue of a 0 of the characteristic polynomial called lambda tilde. And if that occurs k times in the factorization, then this k is called the algebraic multiplicity of lambda tilde. Or to put it in other words, we say lambda tilde has the algebraic multiplicity k. And moreover, there I can tell you, usually we use a lowercase alpha to denote the algebraic multiplicity. So we would write alpha of lambda tilde instead of k. Okay, there we have it. This is the whole definition of the term algebraic multiplicity. First, if we already know that lambda tilde is an eigenvalue of the matrix A, we can conclude that the algebraic multiplicity lies between 1 and n. And of course, n as before is the number of columns or rows of the square matrix A. And moreover, this also works the other way around, because if the algebraic multiplicity is greater or equal than 1, we know it is a 0 of the characteristic polynomial. Hence, it's an eigenvalue of A if we also include complex numbers. But I already told you, we will talk later about the extension with complex numbers. However, I would say for the algebraic multiplicity, we can already deal with complex numbers. Therefore, I would say we can simply sum up all possible values for the algebraic multiplicity. Of course, here the matrix A and the characteristic polynomial are fixed, but we can go through all lambdas that are possible as zeros. This means lambda tilde could be any complex number. So at first glance, this looks like a strange sum, but please note, most entries here are 0 anyway. This is because we only have at most n different zeros of our polynomial, which means most algebraic multiplicities are 0. And for the actual complex numbers that are zeros of the polynomial, we can just sum up the algebraic multiplicities. And because we already know we have n linear factors, the result here should be exactly n. So for example, before we had 2 and 2, so 2 plus 2 is equal to 4. Therefore, this is not a surprising fact, but an important check for calculations. So your algebraic multiplicities added should not exceed n. Otherwise, you clearly made a mistake. Okay, maybe that's good enough for today, talking about the algebraic multiplicity. In the next video, we will combine it with the so-called geometric multiplicity. In general, they are not the same, and it's important to see where the difference comes from. And with that, I really hope that I see you in the next video. Have a nice day and bye bye.